So to talk about atomic particles and the structure of the atom. At the end of last lecture, did this diagram and we talked about how you can know the charge of a subatomic particle, neutrons being neutral, protons positive, electrons negative, that the actual mass of the three particles varies quite a lot. Electron is 2,000 times smaller. Proton and neutron are the same mass. And looking at the numbers again, you can see that if we count the mass as one neutron and one proton, then we count the electron as having negligible mass. So we say that its mass number is 0. So what is going on in that nucleus? Well, every nucleus has to have a proton. But the simplest form of hydrogen does not have a neutron. The only element in the world that does not have a neutron. So all other elements besides the simplest form of hydrogen have both protons and neutrons in their nucleus. Now that the proton is positive, the electron is negative, and they cancel each other out, so the magnitude of the charge is exactly the same. And that's why atoms are neutral, because there are equal numbers of protons and electrons in an atom, and the neutron is neutral. So it doesn't matter how many neutrons we have, that does not affect the charge of the atom. But then there are different elements. On the periodic table, there are 118 shown, and each element has a different number of protons. And that means it has a different number of positive charges. So the number of protons determines the atom's identity. For example, 8 protons always means it's an atom of oxygen. 2 protons always means it is helium. Which element has 17 protons? Look at the periodic table and figure that out. Yes, you're correct. It's chlorine that has 17 protons. So different elements have different numbers of protons. But if it's the same element, they must have the same number of protons, and we call that the atomic number. The atomic number is sometimes shown as a capital letter Z, and it is the number of protons in a particular element. Here's an example, oxygen. If we look at the periodic table, you'll find element 8 is oxygen. The 8 stands for 8 protons. But since we know that the oxygen atom is neutral, it must have equal number of negative charges. So we have 8 electrons. And it just so happens that this oxygen atom also has 8 neutrons, but there are other oxygen atoms that have more or less neutrons. So how do I know that? Well, if I look at the number below the word oxygen in the green block, it shows me that if I add protons and neutrons together, I should get 16, but I get only 15.9994. That is the average of all the different isotopes of oxygen. What is it that holds the nucleus together? I just said that the nucleus was composed of neutral atoms and positive, neutral particles and positive particles. Positives should repel each other. So what's going on? Well, when 2 protons are very close to each other, when 2 neutrons are very close to each other, or when a proton and a neutron are very close in the nucleus, there's a strong attraction. It's called a nuclear force, and it is the strongest forces in the universe. It acts over an extremely small distance, so we call them short-range forces, but it is extremely strong. So what about if this is so tiny, and what's going on with these atoms? Well, we have to be able to measure the size of atoms. And we do that just the same way as you would measure the size of a circle. We look at the radius, and we say that the radius, just like in geometry, is from the center to the outer edge of the circle. In this case, the center would be the center of the nucleus, and the outer edge would be the electron cloud. So the radius of an atom is from the nucleus to the electron cloud. Well, that's a very tiny distance. We can't measure it in kilometers. We can't measure it in meters. We can't even measure it in millimeters. So we found a unit that is much more convenient for the size of atoms, and it's called a picometer. The unit picometer is 10 to the negative 12. It's such a small number, but that's the distance. 10 to the minus 12 meters is the distance between two atoms. So picometers is one of the prefixes that we learned talking about King Henry, who died by drinking chocolate milk. The pico is the word pope in our rhyme, and that stands for 10 to the minus 12. Okay, well, I mentioned it briefly, but there's something called the mass number. The atomic number, remember, was the number of protons. Well, now the mass number is everything in the nucleus, protons and neutrons. So looking at this oxygen atom, you'll see 8 protons, 8 neutrons. So the mass number would be 16. This little blue number below the oxygen is not exactly 16, which tells me there's another isotope of oxygen that has to be averaged together to get this average atomic mass. The mass number, as I said, is the total of everything in the nucleus. It is always there, and it represents the particles in the nucleus. So what are these things that are different? If you have the same element, 2 atoms of it have different mass, that means the number of neutrons is different. And we call those isotopes. The isotope of a particular element will all have the same number of protons and electrons, but the different isotopes will have different numbers of neutrons. And almost every element consists of mixtures of isotopes. How do we show an isotope? Well, there are 2 methods of showing isotopes. One is called the hyphen notation. Hyphen notation is the mass number written after the name of an element, separated by a hyphen. So if we look at uranium, which is capital U at the bottom of the periodic table, and we have a specific isotope of uranium that has a mass of 235, we write it uranium hyphen 235. Another way to write it is called the nuclear symbol. And in the nuclear symbol, you have a subscript and a superscript. And it looks like this. We use the symbol U for uranium. At the top, the superscript is the mass number. So in this case, 235. And at the bottom is the atomic number, the number of protons. So uranium-235 as a hyphen symbol is written as a nuclear symbol as seen at the bottom. So how do we find out how many neutrons are in an atom? Well, we do a simple subtraction. If we know the mass number, we subtract the atomic number, and that equals the number of neutrons. So for example, in this case, 235 was the mass number. We take away 92, which is the atomic number, and we're left with 143 neutrons in uranium-235. A specific isotope, like uranium-235, is called a nuclide. There's also a uranium uranium-238. That's another nuclide. There's also uranium-236. That's another nuclide. Those are different isotopes, but the individual isotope we call a nuclide. Okay, well, let's do a little calculation. Let's figure out the number of protons, electrons, and neutrons in an atom of chlorine-37. What do we know? We know the name and we know the mass number. The name is chlorine, the mass number is the number after the hyphen, 37. What are we looking for? The numbers of each of the subatomic particles. How would we do this? Well, we know that the atomic number is equal to the number of protons, and that in a neutral atom, the protons and electrons have to have the same value so that the pluses and the minuses add up to 0, making it neutral. Okay, we can do that. The other thing we know is that the mass number is equal to the number of neutrons plus the number of protons. The mass number is the total number of particles in the nucleus. So how would we calculate it? Okay, the mass number of chlorine, 37, minus the atomic number of chlorine-37 is going to give us the number of neutrons in chlorine-37. So in a simpler form, mass number minus atomic number gives us number of neutrons. And that's just showing you what each of those means. So if we take 37 as the mass number and we subtract the atomic number, which we can find on the periodic table next to chlorine, we subtract 17 from 37, we're left with 20, which means that an atom of chlorine-37 is made up of 17 electrons, 17 protons, and 20 neutrons. And if you notice, the number of neutrons is not the same as the protons and electrons in this particular isotope. I'm going to stop right there.